And there are certain terms that you might find a bit alien to you, like draw the structure of a 2 degree of freedom feedback controller. Okay, so I just explained why 2 degree of freedom, because you have both the pre-filter F and the controller C. Alright? And these are all defined in your part 2 of the reading that you're supposed to go through. Okay, so please have a go at the practice and tutorial questions. Alright, next what I'm going to do is show another simulation about how changes in the plant will affect stability. Okay, so if you just look at this particular simulation over here, again a closed loop system, controller C, plant, P0, okay, and you input of cows. So what you want to do, effectively this is actually a pendulum plant. So you want it to move from one angle to another angle. Alright. So if it was my original plant, okay, we've got controller C that I already designed for this plant. Okay, this is what the pendulum will do. Very nice. Well controlled. Okay, but let's say if our pendulum has changed. Okay, through wear and tear it has changed. So there's some additional gain to my plant. So instead of L being CP0, my L is now CP, whereby my P has changed. Okay? Alright, and it's no longer stable. Alright? So this is what we're trying to say effectively, And how do you tell if your controller C that you have already designed for your original plant P0, okay, still stable? What you do is you look at the Doyle's stability criterion. Alright, just check Doyle's stability criterion and you can tell if under a change of dynamics in the plant, even some sort of small noise, small perturbations, but the system still remains stable. Okay, so you can check that Doyle's stability criterion. Okay. Robustness using sensitivity function and complementary sensitivity function, right? So let's just look at one example of how we apply that to practice. Okay? So as we've said, there are various stability margins, and they measure how close the Nyquist plot gets to -1. Okay? There are three margins: gain, phase, and vector margin. Alright? In control score, there were some past exam questions that told you to draw the Nyquist plot L and define the margins. Okay, so this is something that you ought to be able to do. Okay, next. Alright, this is our 2 degree of freedom controller CS. So in the past, we used to say that the controller would be a pure proportional gain, but now we're saying that the controller is not just a gain. Alright, so there's frequency, could be a PID controller. Okay, where CS is the proportional gain KP plus an integral gain KI over S integrator plus KVS over certain time lag S plus 1. So this is a proportional gain, this is your integral gain KI, this is your derivative gain KP for PID controller. Okay, we'll cover a bit more detail on how you can tune the proportional gain your integral gain and your derivative gain. Alright, but just note here that different PID gains will result in a different performance in terms of stability and robustness. Alright? Okay, and what else is different is, you used to say that L0 is just C times P. Alright, but with a PID controller, obviously you see S in there, the frequency terms in there. So L0S is now CS P0S. Alright? Everything else remains the same. Okay? The definition of sensitivity function and complementary sensitivity function remains the same. Alright, considering your P, the plant, your pendulum. Okay, you can draw a Nyquist plot, remember that, for this particular plant. Alright, if you do that, this is the Nyquist plot, this is your L naught. Okay, L naught which is CF times P0S. You can also draw the body plot of S and T. Okay, so for those who have notes in black and white, this curve on top is S, and this curve below is T. Okay, and you can observe that T is approximately 1 at low frequencies, and S is approximately 1 at high frequencies. Okay, and with this, you can check where the crossover region is. Okay, and whether there's any peaking in S and T. Alright, and that will actually tell you something about stability analysis of the pendular state. Okay, so pendulum is not really very interesting. Let's move on to another example. This is just P approximately 1 at low frequency, and S approximately 1 at high frequency. Okay? So another example, if you remember about the control of the knee joint. Alright? In this particular example, we have a controller, an actuator. There's something to provide motion. Okay? You can add that in front of the plant, P naught as an MS, which is actuator. Alright, similarly, a PID controller over here, CS. Okay, and you can define that your new open loop transfer function is C times M times P naught. Alright, we want to understand what will happen if you were to change the gain of the system, right? So under nominal gain, if you were to plot the Nyquist plot for this nominal gain, this is what you see. Okay? And in MATLAB, under nominal gain, you can plot the Bode plot, S and T. So you start to see a peak over here, a small peak. Okay? If you increase the gain of your controller, so this increased gain scenario, you see that the Nyquist plot is now magnified. Okay, and what do you see for Bode plot of S and T? You see this. More significant peak in S and T. Alright? And if you increase the gains even further, so the next slide is telling you about touch gains. In fact, we are very close to -1 point here. Okay? You might go into instability because you can see a very big peak here at -180 degrees. So this is your negative real axis. Alright, so this example is to show you how you can make use of MATLAB. Okay? To plot the sensitivity functions and be able to tell if your system is sufficiently robust. Okay? So what are all these plots? If you haven't written down what they mean, you wouldn't understand what they mean. what they are saying, right? Okay? So basically for the control of median angle, all the plots are talking about nominal gain, increased gains, and large gains. Otherwise, slowly move from stability to stability. Alright? Summary or design. Okay? For this lecture, we talk about effect, stability, robustness, performance, subsequent response. Okay? We also go into loop shaping L. We're going to transfer function L. Okay? What are some of the benefits of having feedback in your system? You're able to reject disturbance. You can ensure robustness in the system if there's perturbation. Alright, you can work on the bandwidth improvement of when your system is supposed to move in a linear way. Okay? You want to skip all of this summary. The reason why we summarize and we repeat all over and over again is because, as I told you, this is a very theoretical module. Okay, and as much as you deleted this may come out in exam. You go through a past exam first. Alright? So there's a reason why we're repeating this. Hopefully, first of all, to try to help you understand what is it that you are learning. And secondly, to try to help you follow the flow. Alright, so if you can understand the first part of the lecture, subsequently it should be easier for you to next lecture. Alright, we say that there are 4 factors in your design: accuracy, robustness, stability, and speed. Yeah? So, in addition, we also like to be able to track the common response, reject disturbance, and eliminate measurement noise. So, you can track the common response very well, alright, and attenuate and eliminate the disturbance, as long as the gain the closed system remains high. Okay, and you can take out the measurement noise via measurement noise sensors. Okay, so what's the problem with having high gain? So if you will just increase the gain so large, one thing is of course the system will be unstable. Alright, you may exceed the limitation of your plant capacity. Okay, and you have amplification of measurement. There's no need to draw this diagram. Yeah. I'm just drawing this so that you understand that we do have, you are considering noise in the system. And when you have high gain, N, which is the measurement noise, will go through this controller C and will be measured. Alright? Okay, we move on to design issues. What are the design issues we have in design? Okay, our targets that we want to meet is close to stability. Okay, eliminate disturbance attenuation. We want good command response. We want robustness, stability of performance. Alright, we have problems of plant capacity and measurement noise. And we did talk about what is K, what is control function, how is CP. K, what is the stability function? This is one over of L. Okay, and how does this relate to your individual targets and limitations? So what we're going to do is we're going to review, as I've written here, review the design targets and limitations in greater detail.